Good morning, everybody. Welcome to Math 365 PDE. Apologize for the late start today. So Bill has written this really nice write-up. So thank you for this of Logan 4.2.13, right? This homework problem that or this book problem that I just decided to do one day, and it actually turned out to be quite complex. And this write-up that you've done is quite nice in that it really fills in things that I didn't talk about, including how to exclude negative and zero lambda, and also discussion of boundary values. So I highly recommend that y'all take a look. It's like it's really well written. So seriously, like, check it out. But for today in class, oh, let's see. Like, I want to blow your mind somehow, right?
Do it.
No, I'm ready.
So I mean, I guess we can still stay on separation of variables here, but I know, but I want to move into like a higher dimension. So like move into flatland, so dimension 2. And eventually we want to talk about heat diffusion, maybe on a disk instead of a rod. So still modest goals, but even before doing that, we need to be able to do something like solve Laplace's equation, say with u restricted to the boundary of our domain being a particular function. So why is this, remember Laplace's equation being in standard coordinates uxx plus uyy. So now with two space variables. Why is this preliminary to solving like heat equation on a disk? Well, you have your standard heat equation, and heat equation on a disk will look like time derivative is k times Laplacian of u. So if you wanted to take like the steady state solution or like the long time solution, so what's steady state? That's where the time derivative of your heat distribution is 0, so it's no longer changing in time. And this would, of course, just mean that uxx was equal to 0, so u was just ax plus b, with capital A and capital B being determined by your original boundary values, perhaps. You even saw this in a demonstration the other day where you could see, like, as time went on, the heat equation was sort of settling into the linear steady state. But now in 2 dimensions, instead of the steady state being this trivial equation, you get steady state giving you this Laplacian of u equals 0. And instead of just having a 2-point boundary, your boundary is just going to be like the boundary of a planar domain. And if you let the boundary be kind of arbitrary, like an arbitrary smooth domain, then you've already got a really hard sort of graduate level problem. But in this special case where D is like the unit disk, so x in R2 such that the distance from x to the origin is strictly less than 1, it's open connected domain, the unit disk, and its boundary is therefore the unit circle. then we can actually have a chance of solving this thing. And so this is the question that I want to confront today. And I'll remind you, remember this Helmholtz equation. So we've already found product solutions to that, you know? And that was something that maybe we could even use like a refresher on or something. But you know, back in the dark ages where we weren't quite so happy with, you know, really like how fast the class was going or something. But so in some way, this equation is easier because it's lambda equals 0. But in another way, it's a lot harder because I'm not looking for only product solutions. I'm looking for a full solution to this equation, the full Fourier series, with a given boundary value. And that's what we're going to do today and maybe tomorrow. So with all that out of the way, let's give it a shot. And so we'll try to use this separation of variables technique, and we'll instead of changing coordinates, we'll just assume that we're in polar coordinates. I think I've said this before, but if you want to do separation of variables, you can really only do it on a rectangular domain. And if you're working with just this straight line with two endpoints, that's not an issue because every interval in the line is like a degenerate rectangle, right? But if you're now in R2, then among all the shapes you can make in R2, rectangles are kind of, they're not that interesting. But the least interesting shape that's not a rectangle is a disk. So you're not really going to do a separation of variables with x and y with this disk. You need like a rectangular shape. But this is a rectangle in polar coordinates, right? So if you look at our theta space, then the unit disk is just theta goes from 0 to 2 pi, and r goes from 0 to 1. So you've really just got that rectangle.
That blows my mind.
It's only the first few minutes, but yeah. It's blowing your mind because of the way you've been taught coordinates.
Yeah.
So you've been taught coordinates like you've been taught coordinates like everything is the xy plane, and all the other coordinates are kind of like imposters that are sort of living on the xy plane. Somehow that's how I kind of feel like it, but the way, like a way you can conceptualize coordinate changes, mathematically, is to say, look, like I'm not saying this is the best perspective, but it is maybe the perspective you take in geometry or something. Like, so if you take this unit circle, this domain D, then so what's the coordinate change? Like when someone writes x equals r cosine theta, y equals r sine theta, what they're doing is they're making a function, right? It's like a function g of r theta equals xy. So isn't this like a function g that takes you from the rectangle to the domain? And so if you've got like Laplacian u equals f with u in these coordinates, and if you want to properly write this equation in polar coordinates, you really have to write it back here on this domain, not on that domain. So what you really have to look at is like, you've got maybe a new function v of r theta. That's what you'll see people write down, but the difference, but this isn't like, 100% honest with you, right? Because the domain of this function is this. The domain of this function is that. And that's not quite two functions. They can't really be the same if they have different domains. But what you're really doing here is that if you take v composed with g of r theta, then the output will be the same as u xy. Not really wanting to spend like a long time, lecturing on coordinate changes or whatever, but like if you do like integrals or whatever, like an integral of a function on this domain, what you're actually doing is an integral over here, and you even see your bounds of integration go from 0 to 2 pi, or goes from 0 to 1. But this domain is not equal to that domain. The areas are different, so you have to include this factor of determinant of that transformation. So you see, that's where all that stuff comes from. All that to say, instead of worrying a priori about writing f in xy coordinates, we'll just assume that we're already kind of back here, and we'll assume that that f is a function of theta, where theta goes from 0 to 2 pi, and necessarily f will have to be 2 pi periodic, right? So f is like a 2 pi periodic function on this axis, if you like. Or the way you'll really be thinking of it, though, is like it's a function restricted to this circle. Either way you want to conceive. Without maybe belaboring that digression anymore, this in polar coordinates. What was our formula? This was u or r plus 1 over r times ur plus 1 over r squared u theta theta. I mean, if you think about it, these are like, I mean, this is all on the rectangle, right? Go in direction r, go in direction theta. Like you're doing these usual Euclidean derivatives on the rectangle, but these compensation factors are, just giving you the relationship. Or another way to say it, like I could just choose Cartesian coordinates, theta and r, right? And I could write urr plus u theta theta. But that's not the Laplacian in polar coordinates. That's the usual Laplacian in Cartesian coordinates, just with different names. And so this, this relationship comes from the chain rule, comes from that function that relates the two coordinate systems. Yeah, that function g that I wrote. That's right. And let's check the chat. Oh yeah, did I get that?
Yeah, I think the G goes on the other one. You do G to make r theta into xy, and then do U. It's the same.
Oh, I've got the sound blocked.
Oh, sorry.
Oh, Bill, do you want to say your comment again?
Yeah. you do g to make r theta into an xy and do u to it, and it's the same as doing v on r theta. I think you had the g on the v.
Yeah, I still had you blocked because of the audio, no, I'll take the time to look at this. We had g r theta equals r cosine theta, r sine theta. You had u, xy, and v of r theta. And Bill says maybe it should be v equals u composed with g. So v r theta is supposed to be u. Because now they're both functions of r theta. Yeah, I think I misspoke. So I think you're right. Thank you. So this is how you could define function v, by taking u and plugging in the coordinate change. And now they have the same domain. So u, correspondingly, uxy should be given by taking the inverse of g. So you want to take like v composed with g inverse, right? And so this is how the change of coordinates gives us the different functions of the different domains. So this is like more modern, and this is like more classical. Okay, thank you. So anyway, now that you're on a rectangular domain, you can truly separate these variables. So I can take, following the Logan text, we assume we're down in polar coordinates on the rectangle u r theta, and let us write it as function y of r times function g of theta. And so this, by now, I think you're kind of familiar with just simply plugging this into the equation and getting the product equation. And so what you're going to end up with is negative r squared y double prime over y plus y prime over y times r squared y double prime plus, r times y prime over y equals g double prime over g. And therefore, they must both be equal to a separation constant given by lambda. Skipping a couple of steps that I know you can all do. Just plug this into that equation, and you see that you get y double prime times g plus 1 over r, y prime times g plus 1 over r squared, y times g double prime. Then you divide through by y times g, and then you'll have to multiply through by r squared. question? No. We're just, I mean, you're calling it negative lambda, and lambda is going to be non-negative. That's what's going to happen.
Always.
For this problem, yeah. Not always. I mean, for any particular problem, you have to look at the actual equation that you've got and then kind of, you know, do the argument. You said no thanks. But this is just skipping a couple steps, going from here straight to there, but quite standard and straightforward. So this gives you two equations: r squared y double prime plus ry prime equals lambda y, and secondly, it gives you g double prime equals minus lambda times g, just setting both of these individually equal to minus lambda. And g carries with it some implied boundary conditions just from the fact that f was a periodic function. So it has to be true that g of 0 equals g of 2 pi. And for a second order equation, you like two boundary conditions, but if the function is periodic, then so is its derivative. It's no big deal. And this is actually enough to force a form of lambda. So the strategy is I'm going to solve equation 2 with the boundary conditions, and then I'm going to use my result for lambda to find all the product solutions for equation 1. And, you know, I consider just sort of skipping to the end and showing you what's lambda, but this is kind of interesting, so we'll go ahead and show it. I will skip the part where we exclude lambda less than 0. I mean, I think you're all sort of pretty good at that. Like, you can do this with an energy argument. You can do this with an energy argument, and you'll see it quite quickly, because if you look at y prime going from 0 to 2 pi, you'll get 0 from the equal boundary conditions, right? Check that out. But I believe Rayleigh quotient energy argument will give you that this can't be negative without much work. And so what I'll handle for you is, what about the case lambda equals 0, and what about the case lambda is positive? So lambda equals 0, I mean, I just get g of theta equals a times theta plus b. So what g prime of 0 equals g prime of, I don't think that's true.
Or is it A has to be 0 and B to be anything?
I think it's the opposite. I think, yeah, you know, you're right. It has to be 0. So this is giving me g of theta equals b, and so b is like a constant times 1. So this gives me like g of theta equals 1 as my fundamental, or like my basis solution. My one independent solution. So g of theta has to be a constant. I'm just saying, like, I'll put in the constants later.
Oh, yeah.
Yeah, yeah. I mean, you kind of quickly get that a has to be 0 from g0 minus g2 pi equals 0. And this equation is vacuous, doesn't tell you anything. But just sort of keeping track of my list of, so if you want to be more formal, this is like a basis vector for the lambda equals 0 eigenspace. And then you'll have different basis vectors for the different lambda eigenspaces.
Positive next.
Yeah, so positive next. And in this case, let's write following the book's notation, so lambda equals p squared since it's known to be positive. And you just solve the equation as usual. So g of theta must be sines and cosines, right? So a cosine p times theta plus b times sine times p theta, and here's g prime. So this is a times p, negative a times p times sine p theta plus b times p times cosine p theta. And so you just write down these two solutions. And what you get is I mean, if you let me skip like a minor amount of algebra. So what you're going to get from, remember, these are our equations. And so what you get is that 0 equals a times cosine 2 pi p minus 1 plus b times sine of 2 pi p. And you get that 0 has to be a times sine 2 pi p plus 1 minus cosine 2 pi p times b. So where's that coming from? So 0 equals g of 0 minus g of 2 pi. G of 0 is a plus 0. So that's where this factor of a is coming from. And g of 2 pi is a cosine 2 pi times p plus b sine 2 pi times p. A priori, you don't know that p is an integer, so like 2 pi p isn't going to give you 0 or 1 with cosine or whatever. So you end up with exactly this, and similar with taking the derivative. And you'll be factoring out, like dividing through by p since it's bigger than 0, drops out of the equation. And so a and b have to,
Coefficients have to be the same.
well, a and b have to be such that this equation is satisfied. And so this is a linear equation, 2 variables and 2 unknowns. So the reason why I'm showing you this is that, and you see this in Bill's write-up too, the reason I'm showing you this is really linear algebra problem. So this is really 0 vector is matrix times AB. And matrix given by these coefficients, you know. And so this has to have a non-trivial solution, right? A and B can't both be 0, or G is the 0 function. So you get that the determinant of this function has to be 0. Which gives you this condition that cosine 2 pi p minus 1 times 1 minus cosine 2 pi p minus sine squared 2 pi p has to be 0. That's the point.
Wait, Ken,
Yeah.
do you explain why we want the determinant to be 0? Doesn't this determinant being 0 mean that there is no solution?
The determinant being 0 means that this matrix is not invertible, which is exactly what you want. If the determinant were non-zero, this matrix would be invertible. Right, if I call this matrix A, and if this determinant were non-zero, I could write that 0, 0 equals A inverse times 0, 0 equals AB, which would imply that A is 0, B is 0, and therefore that G of theta is the 0 function, which is the opposite of what we want. So we want there to be a non-trivial solution to this equation, which would mean the determinant of this matrix would have to be 0. And so do the algebra, work it out, and realize that cosine 2 pi times p equals 1. Yeah, that's right. So cosine theta is equal to 1 when theta is a multiple of 2 pi, and so that's telling you that p has to be some integer, and in fact, I guess any integer will do. But then lambda is going to be equal to p squared. And really, I think that, so the eigenvalues are lambda equals 0, 1 squared, 2 squared. So yeah, you can take, any integer, but we're learning that this is A times cosine n theta plus B sine.
So do we have to add that to the solution where lambda is 0?
So this is the eigenfunction where lambda is n squared. Like multiple of this times multiple of that. And the eigenfunction where lambda equals 0 is g0 equals 1. So yeah, you'd add them together, but you're looking for product solutions, not just g0, g1, g4. So you also have to find the solutions to function y. Okay. So let's find the solutions to function y. And the truth is, you've seen this y equation before, both on some of you in book problems you were looking at, and also in a previous lecture. So the other equation was r squared times y double prime plus r y prime equals lambda y, and but now lambda is n squared. And so this is an example of something called a Cauchy-Euler equation. It's the scale invariant equation. We talked about this, like when you change coordinates, the two derivatives give scaling by like, 1 over r squared, and you've got over r squared times distance squared here. You've got 1 over distance times distance. So this equation is invariant under scaling transforms of coordinates. With lambda equals 0, solutions have to be a linear combination of y equals 1 and y equals natural log of r. And we're again seeing this polar coordinate phenomenon where this is really a solution for r not equal to 0. But actually, we seek solutions that are well-defined and smooth on r equals 0. R equals 0 is a coordinate singularity for polar coordinates. So this, this solution is not sort of relevant to us. So I'll just kind of not go on to a long discussion about how to derive it. It's the y equals 1 solution. It's a little bit more interesting. For n bigger than 0, the two solutions are r to the n and r to the minus n. Yeah. Oh, it's n squared times y. Thank you. Yeah. N squared is equal to lambda. And so there's a whole, theory for how to solve this in the same way that there's a whole theory for how to solve that. Here you solve the characteristic equation. Here you solve something called the indicial equation. And like in this case, these are what the solutions look like. I gave a different argument last time I presented this. We're showing it with scale invariant. You might then look at so-called homogeneous polynomial in one variable. But I won't do the digression into the ODE to look at that. There's a brief appendix in the book that kind of shows you the three cases like by solving that equation. The Wikipedia article is even better. The Wikipedia article on Cauchy-Euler is actually extremely good. So I'll really kind of like to put this on the same footing as being able to write down the solution to that equation and not spend lots of time in the PDE class on it. But for here, what do our implicit condition at r equals 0 tell us? We don't want blow up at r equals 0, so we want to take b equals 0. And so I want to be taking, y0 equals 1 and y sub n equals r to the n. And I mean, actually, of course, you can kind of absorb this into that one for n equals 0, 1, 2. And I guess a little remark. So n is allowed to be negative, right? With n squared being positive. So I guess what I really want to say is that since n is allowed to be an integer, I'm really looking at y n equals r to the absolute value of n. Just telling me that when n is positive or negative, n squared is the same, and I'm getting the same answer for that. For that solution, it's kind of like the square root of n squared appearing there in the exponent. Okay, and so this is not a regular Sturm-Liouville problem. It's like a singular generalized Sturm-Liouville problem. So we're not guaranteed automatically that this sequence of functions that we found like will work. Like the Sturm-Liouville theory doesn't directly apply, but they do still work in this case. Maybe we'll talk more about that in a little bit. So I think we want a product solution.
If not R or a 2R, would it be a Sturm-Liouville problem?
No, because
The wrong side.
it's not the wrong sign. Sturm-Liouville is going to require this to never be 0, which is another issue. So like if you, yeah, like if you want to try to do something like, I see what you're trying to do. Like you're trying to do that, right? But even if you did a little modification, like to the constant, you still have the problem where like r is becoming 0. So what you end up doing is like you do this modification, which changes this side, which makes it generalized with the weight function. And then you still have the r equals 0 problem, which makes you singular and generalized Sturm-Liouville. So you can analyze that and you can study it. And you know, the end result is that the eigenfunctions, they work out. So what are you getting here? So you're supposed to arrive at the following equation. Let's check the time. We're pretty most out of time, so we'll kind of just like can conclude it here. The a naught over 2 plus, so product solutions. So the n equals 0 product is just constant times constant. So call that constant a naught over 2. The division by 2 is just so that you get these consistent formulas for the Fourier coefficients, like as usual. And here you've got Rn times an cosine n theta plus Bn sine n theta. And so why is, I guess the question we should ask is like, why is n only going from 1 to infinity instead of going from like negative infinity to positive infinity? That sort of gets back to this question of like, when do the eigenfunctions actually make this complete orthogonal system? And so, yeah, that's what I'm getting at. That's right. So like g of theta is an times like cosine n theta plus Bn sine n theta. And I guess if you take g of negative n of theta,
You get a negative sign from the side. I guess you could include that in the coefficient.
right? So, I mean, I don't have a good theorem to tell you cleanly that, like, this is the truth. But here's the thing. You can either go from, n goes from 1 to infinity and allow yourself to choose a_n and b_n constant, or you could go from negative infinity to positive infinity and have a single constant here. So that's exactly what's happening. So if you let n be in Z, then you just need one constant per eigenfunction. And you could call that eigenfunction Cn. In fact, you could do something like, you could do something like a0 over 2 plus this. And here you could just put like Cn times e to the I n theta. But now you're going from negative infinity to infinity, like you've seen before with complex Fourier series. So one function, cosine n theta plus I sine n theta, times one constant for both of them, but twice as many functions. Or you could do half as many functions, but two constants per function. The Rn is still there, but what does happen to the R to the n? If you do this setup, now all of a sudden you really do need this, because if you take a negative n, your solution is still, your eigenvalue was still n squared, and your solution is therefore R to the absolute value of n. So you can write this function two ways, like with real coefficients and choosing a_n and b_n, or with complex coefficients and going from negative infinity to infinity.
What happened to the solution for G where lambda is equal to 0?
It's right here. The question is, what happened to the solution for G when lambda is equal to 0? The solution for Y when lambda equal to 0 was also constant solution. So 1 times 1 is 1. And then you have a constant you can multiply it by.
So then, with the second version from negative infinity to infinity, that includes the 0 term, right?
Yeah, so I guess you don't need the a0 in that case. And in fact, let's get rid of it. Let's get rid of it. Yeah, thank you. I mean, it's not wrong. What it does if you include a0 over 2, like it changes c0 to like to 0 or whatever. But yeah, you're right. There's no need to include that. So you can either get this doubly infinite series with complex exponents or this classical series with real coefficients. And this is the one that's easy to work with and find an actual solution. So what I'll do is I'll work with this and find a solution, and then, as we did in ODE, convert it back to real numbers at the end. There's also a derivation in your book that only uses real numbers. It's a lot messier and computationally intensive than what I'll show. But either way, it's time for us to leave. So we'll delay that till next time. And I'll just say thank you, everybody, and have a great day.